Okay, welcome everybody to the August Estes Park Group. We've got Ryan and I believe Shane will be joining later from thatDot or Quine going to present today. So we will spare the invitations all around. That would probably take the whole time. But Ryan, I'll go ahead and give you the floor if you want to give a quick intro and launch in. I'll keep an eye for any hands or comments as we go too, and I can flag those for you just in case. So, floor is yours.
Perfect. Let me share a screen here. Um, Hopefully you can see a slide deck that I've got up
Yep.
in front of me now.
Good.
And if I hit play, you can still see it okay.
Yep.
All right. What I especially want to do is introduce folks to the notion of a streaming graph. And today, let's do it in the context of driving AI applications with an event-driven graph in particular. So on terminology, excuse me, streaming graph, event-driven graph, I might use those interchangeably. But that's really what's behind the work that we've been doing at thatDot for, boy, almost 10 years now. So thatDot as a company goes way back, not so far, but the actual work goes much further back than that. So we're a young company bringing streaming graphs to market. But the origin story of this really began almost 10 years ago. And on a DARPA program called Transparent Computing to solve some key impossible challenges in the cybersecurity world. And after achieving stellar results there, the flow outward led to the open sourcing of this project under the name Quine. So Quine.io will let you download and play and use and do all the fun things. There's lots of recipes for getting started, more on that in a moment. But as far as thatDot goes as a company, what we do is we support the Quine project. We have a commercial version of that helps scale that, which we call thatDot streaming graph. And we have an application built on top of that we call Novelty. So it's built on top of streaming graphs for new applications. More on that in a little bit as well. But in particular, streaming graph, and here again, check it out at quine.io. You can download and run everything that we're talking about here. But the main idea is take high volume data from a stream and then use a graph to put those pieces together. Put them together so that you can understand patterns, understand what's important in that data, and then find in real time the graph shape patterns that really matter and stream those out, or collect them and process them a little bit, stream those out to deliver high value to some downstream component. Maybe it's an alerting system, maybe it's a human who needs to see those results. Maybe it's the next step of a data pipeline to process data even further. But the key thing, what makes a streaming graph, is that data streams out. We've had graph databases for a long time that can plug into streaming sources and then be the end of the pipeline where data streams into the graph. But what makes it a streaming graph is the ability to monitor that graph live while it changes and stream results that matter out in real time.
Hang on. Can we interrupt as we go?
Sure.
Is this data that's too big to be persisted? Is that when you talk about streams? Some people say there's some data that has to be hard real time because you can't. Is that what you're talking about, or are we talking about something else?
Real time is a problematic term, like you mentioned. It has gradations of scale, right? So usually what we're talking about in real time is we can find complex pattern matches in streams. We've measured it as low as about just under 8 microseconds, but it's usually sub-millisecond. And the size of the pattern doesn't actually matter. Maybe we talk about that at some point eventually, but in terms of latency, that's what we're typically looking at.
And are you persisting the graph, or is this all just literally in memory in the stream?
Also, great question. Let me just pull up one other deck to help illustrate. Don't mind the man behind the curtain here. Quine plugs into streaming sources like Kafka, Kinesis, and so on. Red Panda, Pulsar, lots of others. But it plugs into those streaming sources, plugs into those sources to publish data out. But to save data down at the bottom, it has a swappable storage layer. And so you can use any of several different technologies. There's more here than what's listed on the slide, or more supported than listed on the slide. You can use those storage technologies to actually build the stateful part of the stream. So the graph that actually stores its data on any of those systems and can pull that data back in to be combined with data as it flows through in streams.
Okay, thanks. Thank you.
Just to help anchor a little bit of intuitions here while we're bouncing around. Streaming data tends to be very high volume, and that's part of the claim here is that high volume data coming in. And graphs have always had a challenge with that. Graphs are powerful. They're very expressive ways to represent data, but handling high volume has always been their Achilles heel. We have tested our streaming graph beyond millions of events per second. And this shows a little bit of the detail on that. So running a cluster that scales horizontally and can theoretically accommodate literally any volume of data. But we've tested it well above 1 million events being ingested every single second, while also monitoring that graph for changes and streaming those results out at about 21,000 events per second for this particular use case. So just as kind of a placeholder of what we're talking about to pin some numbers here. When we talk about streaming graphs and high volume data coming in, it is streaming in very high volume. So this represents a scale far beyond a lot of Fortune 50 companies, and just massive scales that we could probably even go further than this, but it's hard finding data that is actually driving that fast. So if pinning those numbers helps a little bit to anchor some intuitions.
Mm-hmm.
By the way, all the triangles
and
that
so
show up on the plot.
wait. Sorry, I'm still trying to get my head around this. So most of the million that are coming in do not get persisted. You do your magic in the stream, persist the 21,000 and keep going, or are you actually, can you even persist 1 million events a second?
Yeah, we do.
Wow.
Yeah, so usually they all get persisted. If there are duplicate events, those do get deduplicated, and so sometimes there's some efficiency gain just from kind of that simple deduplication. But yep, we persist it.
Wow.
So that's what we mean when we say high volume data coming in. The streaming part could kind of go a couple different directions. People often have different intuitions for where a graph fits into a stream. And it usually breaks down into 2 categories. So sometimes, like for a data engineer, the stream itself is the graph. And so it behaves kind of like railroad tracks, but it's graph shaped because data flows out of a microservice, gets split up into several other microservices that do their work, and then data flows out of those microservices and maybe eventually merges back together again. Mm-hmm. And so the whole data pipeline, a lot of times, is a graph. And in that sense, the pipeline behaves like these railroad tracks, this graph shape railroad track that data flows along as it's being processed and being turned into whatever it needs to be. But graph databases have gotten us used to the right-hand side of this, which is the data itself is a graph. That if you actually represent whatever your source data is, maybe it starts as JSON or protobuf or CSV, lines in a CSV file or anything else, there's a lot of benefit to actually representing that as a graph to put the connections between data elements front and center and get this richer, more expressive representation of the data itself. So what we're really doing is we're merging those 2 things. And so putting together the railroad track idea that data and instructions flow along together with representing the data as a graph itself. So before I talk too much, I want to pause and just show it to you so you can see it live and see it working and doing its thing. I will tempt the fate with the demo gods here, and let's run this live. But before we do, so start this. I'm going to run a recipe. A recipe comes from the Quine.io website. So this is the open source website. You can go download Quine for yourself at the download link here. If you get the jar file, you could do exactly what I'm going to do right now, which is going to the recipe page. And I am running the Ethereum tag propagation recipe. So this goes into the actual recipe itself is in purple. It's just a definition of configuration. You don't have to read this, don't worry. But it's just a definition of configuration to go connect to the Ethereum blockchain, pull that data down, build it into a graph, and do some interesting things on it. So let's see those interesting things. I've got Quine running here. This is the exploration UI that lets us go explore and look at the graph. A few other options along the left bar here that we don't really have time for. But here we go. We've got some data coming in. This is blockchain data. So the first thing we're looking at here is the chain of blocks. Because I really like to tempt the fate, we are just plugged in live to whatever is happening on the Ethereum blockchain right now. I don't know what's here. It's just whatever's happening right now. So here's a chain of blocks. Each block is preceded by a previous block. If we mouse over this, you can see some of the properties on each node. Quine supports, in general, a property graph model. You don't have to read what these are. I just wanted to show that here are some properties showing on a node. But to get a sense of what the structure looks like, we'll explore a little bit. Each block is mined by a certain account. So here's the account ID for that block. Down here, we join a second source of data. There's actually two different sources being merged in this recipe. A second source of data to get the transactions in a block. So these transactions has a little bit more than I'd like to look at. So let's back up a step and limit our query to only 3. So here are 3 transactions that were a part of that block. And each of these transactions also has a bunch of data about it. So details about that transaction, just blockchain related details, the hash, the block number, the chain ID, and so on. But each transaction also goes from some account into another account. And that's kind of what makes up the blockchain. So this structure is being built from 2 different continuous streams of whatever is happening right now live on the Ethereum blockchain. So that's cool. But so far, this is basically just graph database kind of functionality. I said a moment ago that the value of a streaming graph is that data streams out. So let me show you what that looks like. This recipe is set up with what we call a standing query behind the scenes. That standing query is monitoring the graph, watching for any changes that match a certain definition that we've told it to watch for. And whenever it finds an example of one of those changes, we get notifications, we get results that get published in real time. So let me pull up here and show an example of what that looks like, where I'm going to try to find a couple. Let's do it like this. Let's take only the upstream. I want to find a couple interesting accounts. So here's 10 accounts. For demonstration purposes, I'm going to grab these and just move them way over here. Because what we're going to do, let's say just for the sake of argument here, that we are suspicious of these 10 accounts, and that we would like to know if money is flowing through any of these accounts. And so what I can come in and do here is I've got a right-click menu available that is contextually aware. It's defined as part of the recipe here to say that for certain types of nodes, give me different quick queries queries that run anchored at the node that I clicked on that go and execute any arbitrary query that I want, and then do something. In this particular case, what I want to do is I want to mark an account as tainted. If I mark one of these accounts as tainted, I have a standing query in the background that will follow the money, if you will. So let's see that happen. Marking it as tainted is just a matter of setting a property on that node. When I do that, I get a bunch of other things popping up over here. This is going to continue to jump around if there are more new transactions coming in. So if you see it bounce a little bit, it's because there's live updates happening. But all I did is I marked tainted equals 0 on this first account. Hey, there's a new one. So I marked tainted equals 0, and the standing query behind the scenes is actually running to check if that transaction is in a validated part of the blockchain. So is it merged in and on the validated block? So looking at the graph structure there. And then it's following that in and out flow of money and marking each next account as also being tainted. So the first one had a tainted score of 0. This account is 1 hop away, and now it has a tainted value equal to 1. If we continue to get more and more accounts, you'll see the tainted value go up higher and higher. It's going to be whatever the shortest path is. So this is actually an interesting case where this tainted account has a score of 1, and it moved money into this other tainted account. But because there's a shorter path to this one, it still has a tainted score of equal to 1. So as transactions happen, as money flows, new accounts get tainted, and we get real-time notifications, which then show up and animate in this UI here. These notifications can also stream out to other systems and literally do anything. They can call back into the graph whenever there's a notification, which is how this propagation algorithm is working. And if I taint any other accounts, then we would see something comparable happening for their flow of money as well. So this guy is now tainted also. And so there's a new transaction being pointed at for this guy down here, who is now only 1 hop away from a tainted account. And we can see the flow of money as it moves through all these other accounts as well. So this is just an example. This is all implemented on the recipe that's on quine.io, but it's an example of taking a stream of data, building it into a graph, and then having that graph be monitored in real time for its changes. And in this case, any of those changes that matter are tainted funds flowing through the blockchain, and they turn into real-time notifications that we can do anything we want with. And I did just a touch of sleight of hand to help animate and demonstrate this. I actually ran a little Java bookmarklet that is a subscriber to the notification stream of results coming out. So it makes the browser subscribe to those results so that we can animate it. But any system could subscribe. You can publish these results out to a Kafka stream or do anything else that you'd like. So that's the streaming graph, data streaming in, building a graph, a stateful graph, and then monitoring it and streaming those results out. So this on its own is super powerful. But what I'd like to show you next is actually building on top of this to go in the next direction. Let's talk about how event-driven graphs and streaming graphs can actually drive AI applications. I want to show you a few other capabilities that we have behind the scenes for this stuff as well. We'll look at 3 examples for driving AI with streaming graphs. Let's start with just kind of 3 points in time. So classic algorithm, old school. Let's look at current cutting edge techniques powered by streaming graphs. And then let's look at a third example, which is where are things headed? What's some next generation capability that is powered by streaming graphs under the hood? What that translates into is our classic algorithm. Let's see a fast version of PageRank. For the current cutting edge, let's talk about graph neural networks and what integration with that looks like. And then for the next generation algorithm, let's talk about novelty detection and streaming anomaly detection using graphs. So first, PageRank. This is an old school classic algorithm from 1996. If you really get far into the literature, you can point to references from the 1800s for where this idea was in use and circulating. The value of PageRank was underpinning the value of Google for a very long time. The problem with PageRank, well, the value is it tells you what's important. When you've got a graph, PageRank can help you figure out what is important in that graph. The classic example is pages from the internet that Google would then rank based on their connection information. Applied to other graphs, you can tune what important means and really get a general purpose measure of, here's a graph, tell me what's important. So that's fantastic, but PageRank is a slow offline batch processing iterative algorithm. And so it's hard to use it in modern day data without having a Google-sized army to go implement systems to do it for you. So there have been extensions to PageRank that make it faster and make it more incremental in its run. And in particular, new approaches that let you approximate PageRank. And there's a formula down here at the bottom. If we look a little closer at that formula, don't worry, we don't have to get too far into this. But what it really points to is taking random walks on a graph and keeping track of how many times your random walks visit the nodes. And then the bottom section of this formula to get approximated PageRank is a bunch of constant values that are just parameters for how you do it. And if you're just trying to get a relative understanding of what's important in the graph, the actual PageRank score doesn't matter. And all those constants we can just cross off. And so what that gives us is a very simple way to do relative PageRank by just doing random walks on a graph. As it turns out, random walks are this incredible superpower of mathematics on graphs. They are used in so many different categories, from PageRank to graph neural networks to different kinds of embeddings and collaborative filtering, recommender systems, link prediction, so many other kinds of things. But just to level set and make sure we know what we're talking about with a random walk. If you have a graph, a random walk is just what it sounds like. It's pick a point in the graph at random, or pick all the points in the graph, and randomly follow one of its edges. Then randomly follow one of its edges. Then randomly follow one of that node's edges. You trace a path by randomly choosing edges at each step. Do that once, and you'll get this red path through a graph. Do that again, randomly pick some edges, and you get the green path. Do it again, you get this orange path. Do it again, we get this blue path. So enough random walks, and you start to cover the whole graph, and you start being able to measure how many times a random walk visited a node. And if you do that, you get an approximate relative PageRank score. And so that's a measure of what's important in the graph based on its connectivity. So let me show you that live. Let's do, I could have just left that running, I guess, but let's do that Ethereum example again. So we'll ingest some data there, and we'll take a look at what that is. The structure of the data, again, just looked like this. These are the tabs we had open a moment ago. The structure of the data looks like this, but what we want to do actually is let's just ignore the content of this. All I really want is a graph shape. I wish I wouldn't have restarted this because sometimes the Ethereum blockchain is slow and takes a little while to ingest enough data to make it useful. But as we've got that data coming in, we want to get enough in here that our graph starts looking a little bit interesting. So let's just see everything. I'll run a gremlin query. All right, so we're starting to get some graph data in here. All right, that's our blockchain data, but just not laid out as prettily. Okay. How much more data do we have? Do that again. Yeah, just show me everything. All right, so this might be about enough. I'm going to grab a query here. Let this tease itself apart a little bit. See if there's anything more. Yeah, we've got a little bit more. I think that's come in. All right, now I'm going to run my query. Let this animate itself out to actually do an embedding. But there we go. I've got query results that just streamed in here at the bottom. I'll show you this query in a minute, but this is running PageRank on a streaming graph, because behind the scenes, we can give each node instructions. We can tell the node to go do some work. Some of the details for how the streaming graph works under the hood is each node in the graph is an independent actor. And as an actor, it can respond to events and do arbitrary code execution. So in this case, we can tell a node to go explore its neighborhood by taking a random walk. And if we do that, like we talked about, we come back with our relative PageRank score here. And this is sorted by that score. We've got node IDs. Quine supports any value as the ID of a node, but by default, it's a UUID. If we squint and zoom out a little bit, you can kind of tell what the most highly connected nodes are in this graph. You know, they're the ones with just the dense edges around them. And so if I look at this, the ID of this node that looks like it has a ton of edges up here starts with 2792. That's the first one in our list. So a high relative PageRank score because it's so highly connected. If I look at this one, this is what I would guess, would be the next important node just visually. This is FA57 is the start of the ID there. Here you go, second on the list, FA57. Oh, I just guessed that this one's maybe the third one, 36F219. Here we are, 36F219. Taking random walks on a graph answers the question of what is the most important node in the graph by its connections. We could customize this. We could have it look at specific kinds of edges, specific kind of connections, or even specific kind of patterns. But this is just the simple example, running PageRank on a streaming graph. So these can be computed incrementally. Changes in their results can be streamed out. But let me show you what we actually did to run that. This is the actual query that was run in the background. So this is just a Cypher query. But there's something special about this Cypher query. It has a subquery at the top and then returns ordered results down at the bottom. But just above the middle, we're calling a special function. Call the random walk function. That's where we give an instruction to a node. And because a streaming graph under the hood, each node can take action independently, we can just tell that node n to take a random walk of the length that we specified and explore its neighborhood in that same random fashion that we talked about. And then yield that walk that we can then use to increment counters and keep track of who's the most influential node in the graph. So that's random walk capability built into that incremental computation behind the scenes, but into that streaming graph that is plugged into a live stream of data streaming in. Let's talk about the second use case, unless there's any questions on the random walk side.
Hey, Ryan, I'm still trying to wrap my head around each node can execute code independently. Could you expand on that a little bit?
Yeah. So part of what's special about the design of Quine, I'm going to pop over to another slide deck. So the graph data model is super expressive. Each node in a graph is like a noun, or it's like the subject of a sentence. Each edge is like a predicate. And so we can make these connections of subject, predicate, object structures in a graph. I assume this group has worked with graphs a lot, and this is probably pretty familiar territory. But what's special about Quine is that each node in the graph, under the hood, is backed by an actor. And this is a reference to an old idea from the 1970s. Carl Hewitt developed what's known as the actor model. And the idea behind the actor model is that an actor is a unit of computation. It is a single-threaded little process that encapsulates some state, and nobody else can access that state. The actor only communicates with anything outside of itself via asynchronous message passing. And so you can think of each node in the graph as like its own little CPU, its own little process that encapsulates its properties and its edges. And it can receive messages, like if we're executing a query, that's when one of those actors receives a message to say, here's your query, answer your part of it, and then continue. And under the hood, that's all implemented transparently using the actor model for each node in the graph. That's how we do some of the data storage and the streaming ingest, is that instruction comes to a node, which means it gets received by an actor saying, hey, set your property equal foo equal to bar. Receiving an instruction is an asynchronous message that gets put in that actor's mailbox. Whenever that actor has time on the CPU, it dequeues that message from its mailbox and processes it according to the way that it's programmed. And then, if it needs to, it sends messages out as a response to its processing. As a part of its processing, it might actually write data to disk and save a record that I just changed. So my state changed, and I have a new property that I didn't have before, or I have a new edge that I didn't have before. The data storage model behind Quine actually stores on disk not a full representation of the node, but the history of changes to that node. And so this is a technique called event sourcing. It lets us be very fast in a streaming fashion because the in-memory part computes the delta. It figures out, is there any change from this instruction I just received? If there is, all it needs to save to disk is the small little delta, the change, which is much smaller than a node's whole state. And it gives us this ability then to understand how the node changed over time and have a durable record of how it changed over time. And then if we need to, we can actually just issue a cipher query with a timestamp to go back in time and query what the graph used to look like. So same cipher query, just with a timestamp, and now we see the historical answer for however the data used to be at that historical time, because under the hood, we have this event sourcing technique that gives us a record of changes to that node. There's a lot more under the hood for how all these pieces work, but hopefully that helps answer that question. And in particular, the actor model and thinking of a process behind every single node in the graph can help explain some pieces of the puzzle for the question that was asked.
And another one from Michael Sullivan.
Yeah, I see you support Cypher and Gremlin. When will you support GQL?
Good question. We are working on that right now. We don't have a timeline on it.
Okay, thanks.
All right, so part of the magic that took us in the direction of talking about actors is this random walk function that lets us just hand an instruction to a node to say, go explore your neighborhood, go take a random walk. And after you're done with that walk, just give us, the path back that you got. So that's That's the key piece of how we were doing that, that PageRank, especially so quickly, and how we can do it incrementally over time. Let's go to the second example, past random walk. Let's talk about graph neural networks. Graph neural networks have a huge set of applications. They're extremely relevant to so many different kinds of questions in the modern data landscape, whether it's related to large language models or whether it's other important kinds of AI applications to complement large language models. But graph neural networks are hugely powerful, but oftentimes difficult to operationalize. And so what I want to show here is just a workflow for hooking in a graph neural network process into the graph that we've got running behind the scenes. So if I have a stream of data coming in, let's use our example that we were looking at earlier. If I've got a stream of data coming in from the Ethereum blockchain, we'll say, that continues to stream in, build the graph. It changes over time. But if I wanted to compute similarity so that I could say, given any node in the graph, help me understand what is that node related to? How similar is it to other nodes in the graph based on the graph structure? That process is exactly what I would use a graph neural network for. So with an API call to Quine in the background, I can kick off a random walk process that is anchored at one historical moment in time. So this is important because remember, we're plugged into a stream of data. Data is going to keep streaming in. The graph's going to keep changing. And so especially if you have a high volume of data, a changing random walks on a changing graph can give you some nonsensical results. So with a timestamp, as we talked about just a moment ago, I can query a fixed historical point in the past that is not changing. And I can do that automatically just as easily as I do everything else on a live streaming graph. And so I'm going to make an API call to take random walks on the current present moment, historical moment, just so that I have a fixed unchanging graph to walk while new data continues to stream in. With those random walks, I can kick off the training process for a graph neural network. And then I can take the results of that graph neural network and feed those back into the graph so that I have vectors or embedding results or similarity measures fed back into the graph and saved on every node in the graph. So let's look at what this looks like. All right, we've got our graph running in the background still. It's had a chance to grow and get a little bit bigger. That's great. So let's go to the API documentation. So here's the built-in documentation for Quine's API. REST API calls are how you control Quine and make it do different things, especially live while it's running. So if I wanted to, I could come in here and just see some administrative details about how a node's running. Let's actually, I'm going to beef this up a little bit and just let it work with a little bit more data in flight. Again, well, I missed one. There we go. All right, so that changes the number of nodes that are going to be kept in memory, just so that we can play around with some of the API stuff here. I've got metrics information, I've got build information, process information, but the key piece of the puzzle is actually in this graph algorithms section. I've got an API call here to save random walks. I can save it out to S3, I can save it to a local file, but with one API call, I could tune the parameters, I can tune how the walks behave. This is important for different kinds of applications. But I'm going to use this API call to issue a request and just save a random walk file to a local file. And then I'll use that to train the algorithm itself. To show you what this looks like, I'm going to run this Python script. You don't have to read this. You don't have to understand it. I just want to pull the curtain back so there's no mysteries here. This is 100 lines of Python. This is going to use GenSim's word-to-vec model. And so we're going to take the random walks, feed that data as training data into word2vec to build a model, and then we'll export the vectors. So it's going to embed the graph into the vector space. We'll take those vectors and put them back into the graph. And then we can cycle around and do that continually. So let's see what that looks like. Make this a bit bigger. Let's just go full screen here. So let's run that script, 100 lines of Python, but it's going to compute the vectors by making the API call. So we just saved those to a file. We're done with that. Now we're going through the iterative training process. So this is using GenSim's word2vec. We are training the neural network just locally here on my laptop. But you can see the measurement of loss over here on the right. This is getting updated as the neural net weights kind of explore their local area. That loss function tends to go down over time. That's how we actually do the training for the neural network that's being learned here. And after, say, 50 iterations, our training is complete. We take those vectors and we've just streamed them back in. So if I go to my graph and I pick anything that I was looking at before, so this is some data we were looking at before. Let's just pick a node here. I've got only one property on that node, but if I refresh it, now I can see it has a vector field. And let's just look at its local properties. So you can see in all the glorious numeric detail, I think this is a 200-dimensional vector. Yeah. So this is the vector representation of that node. So it's something that we learned through the neural network. And we did it by walking the graph, training a neural network, and then reading out those vectors and streaming them back into the graph. So here, if I was running this live, and I've got a stream of data that keeps continuously changing the graph more and more, I would want to recompute these vectors periodically so that we can take into account new data. So yeah, just do it again. Makes that API call. Right now, we're generating the random walk. The random walk file is done being generated. We're now training the neural network with the new data set. That runs through that same kind of 50-step iteration process just for demo purposes here. And when that's done, it'll do the same thing that we saw before. It'll take the vectors that have been learned for all the nodes in the graph and stream those back to update each of those properties in the graph. So we don't have to watch a neural network train itself, but I just want to show that loop to give you a sense of what does a graph neural network look like when it's integrated to a streaming graph. The key piece of the puzzle that we highlighted a moment ago is in that API, we have this @time parameter that we can cause a changing dynamic graph to be static for this purpose that we wanted to do, for generating random walks. So query this historical moment while the graph is not changing. As we query that to take the random walks, we feed the neural network, we train it, and can stream those results back into the graph. So that was that process from end to end while data continues to stream, just an API call to hook in this training loop that feeds back into the graph. Any graph neural network questions? All right, last piece of the puzzle, novelty detection. This is where the future is headed. There's a problem with AI algorithms that do anomaly detection. There's a couple problems. They're opaque. They're generally very slow and they don't work on streams. And in particular, they don't work on categorical data. Categorical data is anything that's not a number. And if you have different kinds of applications, especially like in a cybersecurity kind of environment, the kind of data that you're looking at in most cybersecurity environments, but really broadly speaking, almost any environment, data falls into two categories. Either it is a number or it's not a number. If it is a number, you can use traditional anomaly detection techniques and do fairly good. It's still not usually streaming, but there's a couple applications out there. I think Microsoft has one for streaming in numeric data and getting measures of how anomalous those numbers are as it streams in. But if you have categorical data, so it's things like IP addresses, file paths, usernames, email addresses, URLs, any of that kind of stuff, that's not a number. And the typical data scientist's approach to what they do with that is to do a technique called one-hot encoding, where you try to turn it into a number or into a vector. Long story short, it doesn't work very well. It doesn't generalize to unseen data. It causes the curse of dimensionality to just blow out of control. And it's why so many false positives continue to plague the cybersecurity industry everywhere. So what I'm going to show you here is a product from thatDot that is built on top of a streaming graph. And it uses that categorical data directly to build a graph under the hood. It uses Quine. It uses the streaming graph that we talked about with a whole event-triggered actor model basis under the hood. What it does is it gives us a measure in a streaming fashion, a measure of how novel is every observation that I make from a data set. So let me show you what it looks like. To show this, I have to explain a little bit of the context here, the scenario of the data set that I want to show. So the data set here is an old data set from 2009. This is a public challenge data set from the VAST group. The VA in VAST is because this has been thought to be too difficult for automated analysis. And so it's a challenge for visual analysis. That's hard enough. But what the scenario is for this is that we're looking for an insider threat. So that's an employee, in this case, the employee of an embassy, who is supposed to have access to things, but that employee is doing something malicious. They're doing something they should not be doing. So the data that we have to work with is behavioral data. It's about the people and their proximity. So as they badge in and out of the doors of our office floor plan here, so that's what this image is showing, is it's the floor plan of the office where there's an outside door they badge into, and there's a record generated. Each employee, 60 employees, share 30 different offices. So 2 employees in each office. Each employee has their own computer. That's the second piece of data we have, is network records for each computer assigned to each employee. So we've got proximity information because they badge in and out of the outside space to get into the office. Then they badge in and out to get to the classified space. And they don't always do everything they should do of badging in. Sometimes people follow other people. But in general, we've got these kind of proximity behavioral records. And we've got network logs, like what a router would see, flow data about what each computer is doing. And so when we put those together, we've got what's the proximity information for a user whenever there is a network event on their computer. Let's drop out of the slides here for a second and drop out of that previous demo. And I'm just going to run the novelty application. All right, let's go back to the browser. In the browser, this is what our getting started page looks like. we've got some of the same capabilities and UI that we saw earlier. So there's built-in documentation for the novelty app built on top of Quine as well. But we've also got this getting started page. I'm going to choose a data file to get started. It's the behavioral data we were just talking about. So it's badge status, source IP, port, and destination IP. Those are the columns in our CSV. So our CSV has headers. And here's a little preview of what that CSV file looks like. So I've selected my data to come in. I'm going to tell the system, go ahead and learn a transformation. We don't really need this in this example, but sometimes data comes in a form that is not what you actually want to score and feed and record. So this is an opportunity, if you want it, to write a JavaScript function right in the middle here that would take in the incoming line from a CSV called that, and then change it into something else. So you could select some fields. If it's a JSON object, maybe you want some fields and not other fields. But select out some fields, reorder them, turn it into an array of strings is what we're actually going to feed this. In our case, the automatically learned transformation does very little. It actually just flipped the two fields in the middle. But I'm going to stream this in, and it's a CSV file, but we'll just pretend like we're plugged into a live streaming source of that data. But when I hit ingest all records, it's going to start streaming that data in. And you can see it, the counter's going up. Let's go over to the results tab. Here I'm getting scored results. So this plot gets updated as more data streams in. We've got 115,000 events, so it didn't take very long. It looks like we're about done. So our data is here. It's been scored. This first plot is just a sample of the data that came in with its streamed scored results. On thatDot's website, there's a blog post that goes into in-depth. If you search for insider threats, it'll go in depth into this particular use case. And so if you'd like to see gory detail, all the technical implementations of everything here, you can see it. It'll walk through the scenario and point the finger at the final whodunit question, which, spoiler alert, it's employee 30. But if you'd like to go far into the details of how that works and why, you're welcome to. But since I'm spoiling the surprise anyways, here's the top scoring results. This last plot is showing the novelty scores of each item that streamed in after the whole data set has been streamed in. And again, to spoil the surprise, every one of these tie scoring dots is the insider's malicious activity. What you see in common with all these dots is in the upper right-hand corner, the bad guy is exfiltrating data to this IP address that ends in .133. And so each of these were pulled out in a streaming fashion. They're pulled out and scored in real time to say these are unusual. They get a very high novelty score that makes them stand above, head and shoulders above all the rest of the data. And what's happening, and you can see the other commonality here, is the first value in each of these observations procs in classified. When one of the bad guy's colleagues goes into the classified space, he's sneaking into their office and using their computer to exfiltrate data to this .133 IP address. The reason I pointed to that blog post is if you want to see more about the scenario and the story and all the pieces there, you can go see all the details in that blog post. But the takeaway here is that under the hood, we've got a graph. That graph builds up a model of the history of the whole data set. The data set that we've been looking at to score and to see what's happening behind the scenes, all of that with some math over top of it gives us this context-aware fingerprint of every individual, every IP address, every port, all the relevant features of our data so that we can score it in real time and rank all the activity that's happening behind the scenes. So this is a next-gen AI application that solves a problem with a bunch of current techniques that end up being much too slow, don't work on the right kind of data. They don't work on the data that actually has the information that's relevant. And so it's solving a problem using a streaming graph under the hood to hook into this next generation capability of scoring and ranking streaming activity so that we know what's important, where should I pay attention, what should I pay attention to. And with that, I know we are coming up on time.
Yeah.
So I will thank you all for the chance to talk to you and for your kind attention and questions along the way. If there are any others, I'm happy to answer for the minute we've got, or happy to take any more down the road.
Yep. Yakov. Oh, you just disappeared. Oh, you're muted.
Okay, thanks very much for the great presentation. I have a question of two parts. The first part is sort of a business case question. I was studying your use case of thatDot as security of threat detection and so on. And we have basically two parts. One part is analysis to look at the past and at the present as a very near close past and to see what is happening, who is doing something bad. But you always have also then the second part is to do something, to impose your own will, to change the reality, to keep the bad guys out, to correct the error, to catch them by taking action. So the first question is, in your company, do you use the streaming graphs to support and to empower that second part of taking action in a more powerful way?
Yes, we do. What that looks like from our perspective is feeding the critical information at the right moment to downstream systems. So especially in a cybersecurity context, it's tricky because automated action, if you tried to fly 2 weeks ago, you'll understand the pitfalls of automated action in a cybersecurity context. But automated action can sometimes, be a difficult thing to manage. So from our perspective, what that looks like is feeding timely data, timely, relevant, kind of fully packaged, contextually aware results down to whatever system needs to consume those. And so taking automated action might be the job of that next system. Or it might be producing an alert for a human to then go understand, see the context of, and kind of draw a conclusion about which automated action to then go trigger. But from our perspective, it's very, since we're an infrastructure component, in this streaming category, triggering action for us really looks like feeding the relevant data at the right moment, like immediately when it happens, to the next downstream component.
Can I make a comment over here? First of all, I would, in my word, classify that still as you looking back at the past. You're saying what is present, what is there. You're not trying to do something. You leave that to the other actors. Now, I have been researching for the last couple of months, trying to solve problems where we want to acquire information which is not yet there, take action in order to uncover information which is not yet in the system, and to take actions to achieve outcomes which are not yet present. To say, we have a problem over here, and we want to structurally take actions towards it in a human in control, not human in the loop way. Which means that if the situation is already known, then it works automatically. But if there is anything unusual, then the system waits for an expert to understand the novelty over here, and then amplifies this work throughout. So I was studying this in a different application domain, And what distracted me is that the underlying technology which is needed to support that looks exactly like your streaming graph. So it has some slightly different semantics, because we're talking about future that we want to achieve as opposed to things which we know or something which we predict will happen, but not as a result of our own action. But I found that it has you basically need a graph which is growing, where you have standing queries as opposed to queries being asked at when somebody asks a query, and an actor model for each individual node. So I was interested to see whether I actually use the same underlying technology also for influencing the future, to guiding and driving reaching certain goals.
Yeah, we have users who do kinds of implementations that do, say, link prediction, to understand, here's a graph, given the structure, where do we predict is some missing data, or where should there be an edge that's not in the data set. And that's a common driver for the kind of thing that you're talking about, a prediction for what should you do, or what is about to happen, therefore there's something you should do. Also, we've seen a lot of use cases where different forms of risk scoring of what's happening. So it might be infrastructure of telephone poles, throughout a city, that form a graph, and connections in there to understand, well, what are the implications of if this pole, gets knocked down in a storm, it's this one is going to take out power for which we have no backup to a whole neighborhood, or whereas in another point in the graph, a loss of a telephone pole will have 3 backups, ready to support it. That sort of calculation done on the graph representation there for the sake of understanding where does the risk lie, and so then where should the human action be to go mitigate that risk.
Mm-hmm.
Yeah, we've seen those kinds of things for sure.
It's very impressive.
Thank you.
Yeah. So Quine is open source and this thatDot is commercial. Is that the idea?
Yeah, that's right.
Yeah.
So
Okay.
Quine, and the website is quine.io for the open source version. The open source version is fully functional. All the pieces are there. We hope people use it and get a ton of great value out of it. The commercial support that our company provides is especially for when use cases are especially high volume, scaling Quine to support extremely high volumes, or to handle some special capabilities for mitigating supernodes in very large data sets. That's some of the commercial extensions to Quine that is built in and supported by thatDot.
Very cool.
With that, I want to say thank you to you all.
Yeah.
I appreciate
Thank you.
the chance to share.
Very impressive. Thanks.
Thank you.